Okay, welcome this afternoon to where's the title of your slide talk here? Oh, you don't have a title. All right, hold on a second here. Can I borrow this for a minute? Yeah, thank you. I want to get the right name here and the right information. David Anders, who's working with Intel's open source OTC, and he's working with specifically with the Minna board and other open source hardware boards and open source hardware stuff. And what he's working with right now and going to be talking about today is creating open source hardware tools. Welcome, Dave.
Thank you. So to get started here, all the references, a lot of the stuff I'm going to talk about in the slides will be here on our elinux.org wiki under Open Tools. Lots of stuff that I may not necessarily gotten to in the presentation will also be linked there. So if you're interested in creating open hardware tools, this is a good reference page for you to jump off into other items. My name is Dave Anders. I go by Purple Plague on IRC. I go quite a bit of different IRC channels. Often you can see me on Freenode. As Tom mentioned, I'm employed at Intel, and I'm part of the Open Source Technology Center, specializing in the Middleboard Max, or the Middleboard.org program. This presentation is going to be on creating open hardware tools. And we're going to talk about a little bit of background and history of open hardware tools. We're going to talk about what's out there right now that allow you to make open hardware tools and how it's influencing open source developers. And we're going to talk about some challenges going forward that are making things a little more difficult for creating open hardware tools. So to get started, let's talk about open tools in history. Open tools have been used in science as long as there's been recorded history. When you do an experiment, create an experiment, a lot of times you need special tools that don't exist. And as a scientist, you have to create those yourself. These new tools are often shared with other scientists, royalty-free or shared as open. And one of the most famous one is Robert Bunsen. Everybody here has probably used a Bunsen burner in their chemistry class. And he's one of the most famous open source hardware tool manufacturers in the world. Because when he designed the Bunsen burner, he licensed it royalty-free for anyone to manufacture and use. The only requirements that he had were, A, he had to keep the name that it was a Bunsen burner, and B, it had to be manufactured in the safe, quality controlled environment, and that what you manufactured lived up to his name. And so he adamantly defended this, but he allowed anyone that wanted to manufacture it and even sell it and profit off of it could do so as long as they abided by the open hardware information. With that in mind, today we're looking at probably for the last 50 years in electronics, there are tons of commercial solutions for things such as logic analyzers, USB oscilloscopes, all kinds of devices for JTAG. You name it, there's a commercial solution for doing debugging of some type. These all have some limitations. For instance, a lot of them only support a single operating system, which is a big, big minus, especially if you're using Linux and open source. The other is price. Most of these are extremely out of the budget for most makers and hobbyists. So these are out of the question price-wise. And, of course, we have to look at the features and fixes. You find a tool that meets 90% of what you need to do, but you have a special condition that you need this extra 10%. You are not allowed to make those changes, go through, create new features or bug fixes, and submit them back to that manufacturer. Most of the manufacturers of commercial devices are not interested in feedback from the customers like this. So with that in mind, back in 1999, a university in the Netherlands started one of the very first open source hardware projects. It was based on an Intel strong ARM processor. Yes, Intel actually did make an ARM processor for quite a while. And so this was an open hardware project. The entire design, including bill of materials, schematics, Gerbers for this particular project were open to the public. And as I said, it was one of the very first open hardware platforms. One of the very first things that they found was they needed some way to get the bootloader on the flash inside this open platform. And they went out and looked, and sure enough, there's a methodology called JTAG that allow you to put some images into the flash to get started. But the JTAG devices that were available to them cost tens of thousands of dollars at the time. So they came up with a parallel port JTAG dongle, affectionately known as the Holly Gates dongle. This particular device is one of the very first electronic open hardware tools that is combined with Linux and an open hardware platform that make it a very unique item. And people have continued on this, starting with JTAG, and continued to create their own tools to solve problems. The maker-hacker community has changed the way people create hardware and software solutions. The maker community and open source hardware association have created an environment where people are creating new electronics. They're creating programs for Arduinos and Raspberry Pis and BeagleBones, but there are things that can't always be done by software. Sometimes you need a hardware tool to solve that problem. It used to be that a good multimeter would solve 99% of your problems when you're doing electronics. That's not really true today. A lot of the electronics with microcontrollers, PWM, I2C, SPI, all of these interfaces, they require a lot more work in order to debug them from the hardware side. Logic analyzers, there's commercial solutions that literally start in the neighborhood of $150 up to $150,000, depending on what you want. So the maker and hacker communities have gone through and created their own solutions for this and shared them as open source hardware. A good example of this is the Open Workbench Logic Sniffer. This isn't a piece of open hardware that's been created to allow you to do logic analysis. It works for I2C, SPI, half a dozen other things, including CAN bus, and it's programmable and supported under Linux with open source packages such as SIGROC. Another one is the Bus Pirate, and it's a very super simple board. There's some tight pitches on it, but in general, most people can solder this by hand, especially if they have a good scope or something that they can use. But it's completely open for anyone to use and manufacture themselves. There are hundreds of other smaller versions where people have taken things such as a stock Arduino and created their own logic analyzer that's powerful enough to debug I2C running at 100 kilohertz or 400 kilohertz and allow you to get into electronics. Yes, sir? Can you give me an example of an Arduino scope? Well, that's certainly put in there because everybody's got to put an Arduino in everything, so I have to kind of listen to it. So, another item that has traditionally been very, very expensive and out of the reach for most hobbyists is an oscilloscope. For years and years, or actually more like decades, the lowest cost dual trace oscilloscope you could get was in the $800 range. And today you can find some on eBay and such that are $250 to $350. But again, the maker and hacker community has stepped up and created solutions for this. There are such things as the Nano DSO, which actually runs Linux on several versions of it. Others, it's a lower ARM Cortex device that runs a specific firmware, but all of it is open source so that you can work with it. So technically this isn't actually open hardware, but it's open hardware friendly tool that's getting down there where commercial companies are starting to see there's a point to providing these types of items. Again, there's AVR and Arduino solutions that are out there, and a lot of these you can buy as kits from places like SparkFun or Adafruit. And these are 99% of the time, if you have a young adult that's going through and learning about electronics, these are more than enough for your investment to help them understand exactly what's going on. Most of these kits are less than $30. You can get them assembled in the $50 range. So all of these are open source designs that allow you to have bill of materials, Gerber, design files, everything you need to manufacture these and create your own versions of them if you want. There are also pick versions out there as well. A lot of these types of parts you can pick up on eBay or discount vendors and put yourself together a quick oscilloscope that you might want to use. Or if you've got a electronic project that you need something to custom debug whatever it is you're working on, that's where the idea of creating your own open hardware tools becomes very interesting. You have several different solutions. For instance, you can use an off-the-shelf solution, such as this particular one that I designed, and it actually uses a DVI decoder chip, TFP401, and the purpose of this particular board is so that I can debug HDMI and DVI timing. We've actually got on the board itself debug headers here where I can hook these up to a logic analyzer for the red, green, and blue. We have the horizontal sync, vertical sync, data enable, and your pixel clock. And we actually also have a EEPROM, where's that one on here? Right here, that actually pretends to be the EDID for a particular display. So you can actually pretend to be an LCD panel so that you can go through and debug it. All you have to do is basically buy this particular chip, design the stuff around it, and you have a debug tool. So it's easy to find decoders and receiver chips through DigiKey or Mouser for a particular use and build something around it. So you don't necessarily have to design something that reads DVI or reads HDMI. You can use an off-the-shelf chip that already does it to provide you the information you need. The next item is common interfaces. You don't actually need to develop a lot of electronics sometimes. This is a small Allure board that I created for the Minoboard Max. And this was to test the expansion header for the Minoboard Max. The original purpose of the expansion header is to go through to something as an mSATA or a mini PCIe interface, and also to additional USB devices. Rather than create a specific board that has all of those things on there automatically, all I've done is brought them out to standard interfaces, for instance, a standard SATA connector and a standard USB connector. And so you've not really created any electronics. All you've done is converted that over into a standard interface. So if you know your device has a USB 2.0 on it and you're not sure how to test that USB 2.0, simply add a USB 2.0 host connector on there, plug it into a device, and begin testing. So a lot of times you don't even need to create a lot of electronics. It's just a matter of connecting up to commonly used interfaces. Another one is shared tools. This really means that there are a lot of software packages that may have a very specific purpose. For instance, FlashROM is actually a tool that allows you to reprogram the SPI flash on a motherboard for your custom firmware. For instance, if you're dumping UFI and you want to do core boot or vice versa, you can actually use FlashROM to reprogram the firmware. Now, FlashROM supports a USB protocol that allows you to build your own board to program the SPI flash. There are several different shared files that you can go out there and get custom schematics and create these to work specifically with a software package. Another example of this shared aspect is, for instance, the FlySwatter JTAG board. This was built around specifically working with the OpenOCD application to do JTAG debugging and flashing. So you can go out to these software packages and say, what kind of hardware do you support? And usually they'll have that on their wiki page and say, we support this FT2232 or our particular FPGA solution. And you can take that as a starting point for your custom solution. Which brings us to creating your own solution. There are a lot of software packages out there that allow you to do board layout and schematic capture. But because we're an open source community and hobbyists wanting to do development, there are several that we have to have discussed here. The first is KiCad. KiCad is a completely open source package, and it's been under development literally for years, and it continues to become a very robust package. As a matter of fact, this specific week, KiCad is actually being used at CERN and to do small board layout and specialty boards and tools at that location. And they've contributed back to KiCad a large amount of patches, including a recent support for doing differential pairs and impedance matching. So it's a continued supported item that people really like. It does have some limitations. It is not very user-friendly. Typical Linux open source utility complaint that a lot of people say is not very user-friendly. It continues to get better, and I think it's in the next 2 years or so, this will become the standard for both maker and open source developers. The other one is EagleCAD. It is not open source, but it has been the choice in the hobby community for literally a decade because of some very basic items. First, you can get a limited version of EagleCAD for free with limitations. It only does 2 layers, and it has a maximum number or a maximum size of PCB you can design of 80 centimeters by 100 centimeters, I believe. So there are limitations, but there is one big aspect to it. It does run under Linux. They do offer a standard Linux installation for it. So it is very, very popular in the hobby community to use EagleCAD. In fact, companies like SparkFun often provide their libraries of what they've done, so you don't necessarily have to design your own parts. You can download one of their libraries and get things like LEDs, push buttons, switches, all of the minor ICs like voltage regulators. These are already done for you in a library, and you can share these files with other people. So EagleCAD is still at this stage probably the design tool for the hobby community, but we hope to see KiCad replace that in the near future. So the other big thing to designing your own hardware tools is to making sure that you license it. A lot of people will put the design files out there and forget to put the licensing on there. You have to make up your own decision as far as what kind of license you want to put it under. Almost all of the things that I do, I release under Creative Commons, and you can either do it as a Creative Commons for non-commercial use, or you can do Creative Commons for any use that you want. So there's a lot of different variations. You can visit the Creative Commons site to do that and decide which license you specifically want to put it under. The other fact is the Open Source Hardware Association has some very strong definitions about exactly what is open hardware and when you can say my device is an open source hardware device. And you can visit their site as well and get more information on what you can consider as open source hardware. But when you do design something, really, really consider on releasing it as open source hardware. So this really fast cover a lot of things about where we are in the community as far as developing things, and you've seen that the maker community has really stepped up and created some unique tools for solving situations both on cost and for creating it for the open source community. One of the things that's changing is all of the things that we're working on are becoming exponentially more complex. And so initially when you think back in the early 1980s with the Altair and things like that, we had a very, very simple display system. Most of the time, everything was a LED. You could hook up your multimeter and check it and decide whether it's got the right voltage or not. And it's very simple in the aspect that it's easy to visualize. It's either on or off. It's easy to measure with your multimeter, and it's easy to program from the software side. Jump just a few years, almost 5-10 years ahead. You've seen the evolution of the displays where we're using 7-segment displays and microcontrollers to multiplex a single group of GPIO pins or whatever to display multiple digits. So this is where logic analyzers and oscopes become much more beneficial for doing debugging because you have clocking, you have multiple signals, and you have a microcontroller to consider. Even further on, another 10 years, we look at transitioning to LCDs, which become even more complex in the aspect that it has high frequencies most of the time in the hundreds of megahertz, much more signals to look at, and even more complex controllers. So we've seen a progression of very simple display devices all the way up to very, very complex stuff that we're dealing with right now. And what we have to have is an idea that these tools to debug these items has to match the complexity that we're seeing in increasing magnitude. So with that in mind, we're going to look at some design constraints. Most of these things that we're talking about debugging in very complex nature are going to be multi-layer boards, meaning there are actually 4 or more layers needed to create the PCB that you're going to work with. Why is that a problem? Well, as I was saying earlier, EagleCAD provides a free version of the board, but it only supports 2 layers, which means if you want to start doing some of the more complex boards, you need to pay for a more expensive application or create one such as KiCad that does support multiple layers. Each of these layers adds a different set of signals that you will have to deal with and calculations. These are things that traditional hobbyists and makerspace community are not familiar with. They've been limited to 2-layer boards for a very, very long time. Matched lengths. Most of the signals that hobbyists are dealing with, such as GPIOs, I2C, SPI, these are in very, very low signals, most of the time less than 1 megahertz. Sometimes you can get the SPI up to 50 megahertz, but even below 100 megahertz on these, doing matched lengths of your traces is not necessarily a concern. But going forward with the more complex things such as USB, PCI Express, HDMI, DisplayPort, all of these high-speed signals that are often running at multiples of 100 megahertz or sometimes even in the gigahertz range, matched lengths really matter. Again, most of the tools that are free to the maker community do not support easy routing of matched lengths. In addition to the matched lengths, you also have matched impedance. These are complex, not necessarily complex calculations, but calculations that have to be done in order to make sure that the traces are correct. And generally, again, this is not something that the maker community has been experienced with. So there's going to have to be a transition to educating the maker community on how to use these particular items. And lastly is package type. The maker community is very familiar with dip package on a 10th-inch center, and that matches their soldering skills. The problem we're seeing here is a lot of the devices we want to work with are BGA now. Often we'll go to a QFN package, which is a companion to the quad flat pack, which actually has leads. The QFN, the N stands for no leads. So it's very, very difficult to hand solder this with the soldering iron. This has to be done with air or in a reflow oven. So these types of packages are beginning to push out a lot of the maker community in creating their own open hardware tools because of these packages. And a lot of times, the particular device that you may want to work with for your debug tool may not be available in a dip package or even in QFP. It's only available in QFN or BGA. So all of these are challenges that we're looking at moving forward. One of the biggest things that is going to be important in the next 10 years for people doing open hardware is FPGA development. FPGAs have been around for quite some time, and they've been used for a lot of different things, but it's becoming more and more important because software developers are actually transitioning into creating debugging tools that are based on hardware. And this allows you to do a lot of things that you can't do with an AVR or a PIC or a small microcontroller. For instance, PCI Express and many PCIe type devices. To debug and test these are differential pairs. They have to have match lengths, match impedance, and they operate at very high speeds. which puts them out of the reach of most people to create open tools to make debug these items. It's important because there are a lot of libraries already existing for FPGA that already support PCIe, and all you have to do is load that library and create your own software for specific use case. Another example of this type of interface is the SATA and MSATA. These are, again, differential pairs operating at extremely high speeds, and they require different match lengths and matched impedance. And they're not easy. You're not going to be able to put a multimeter or a logic analyzer very easily on this and debug it. So transitioning to FPGAs is very important. Another one is the HDMI and display port. How many times I've gone through and tried to bring up a board where the HDMI wasn't working and I needed to figure out what was wrong with it. And that's what led me to create other FPGA tools specifically for HDMI and display port. So the FPGA portion of it is going to become extremely important long-term wise. So problems with FPGA right now in the Linux community is there's a lot of closed documentation or NDA docs where you can't get anything. So that also means that if you want to create your own tools to work with that FPGA, a lot of times that's going to be restricted. Other things, for instance, when you're creating an FPGA solution to work with a high-speed interface such as HDMI, a lot of the HDMI documentation is closed source. You can't necessarily get it. There are open specs portions of it, but a lot of the details are still restricted. And this is kind of an industry trend. There are other display interfaces like groups such as MIPI that actually provide DSI. They also provide a camera interface, CSI. All of those types of interfaces are closed documentation, which means that you have to be a member company in order to create tools for those devices. So closed and NDA documentation is a real roadblock for creating open hardware tools yourself. Restrictive licensing. We found that a lot of the libraries that we had found to do PCIe or SATA support were very limited on their license. We couldn't open up the remainder of the design because portions of the libraries we were using were closed. So the entire design we were doing as an open source tool couldn't be done because of the closed source library. And also DRM. DRM continues to be a nightmare for a lot of people creating their own tools because it creates a major roadblock on doing development on a hobbyist level. So I've rushed through a lot of this and wanted to give you a really good background and everything. So we've talked about a little bit of history in the fact that open hardware tools is not something new. It's been going on a long time. We've just transitioned from creating lab equipment out of glass and pipe to creating tools out of PCBs and silicon so that we can do our own testing. We found that the maker community has been absolutely fantastic in creating their own solutions, and there's a lot of resources for people to create their own solutions in their garage to do whatever they need to do. And lastly, we've seen that there's a lot of roadblocks and challenges in the future for us in order to continue this development cycle. And it's very important that everyone is active in working towards resolving some of these issues. So there's a strong incentive for open source developers to get in to do open source hardware as well. You may not necessarily be a hardware guy that you've got a whole box of electronics in your garage and you do something on every weekend. But if you're a software developer, you've got a board, embedded board, and it's not working, and you want a tool to solve your specific software issue, there's an incentive for you to get involved and create that yourself and continue the idea of open source into the physical hardware. And even if you're not interested in creating your own open hardware tools, there's a strong incentive for you to use them. Software applications such as SIGROC have a wide variety of tools that it supports. And so if you need a logic analyzer, oscilloscope, or some other small tool, before you go out and then spend $250 or $500 on that tool, check first to see if there's an open source alternative available so that you can help support the community. So, and lastly, all of the things that I've talked about, plus a ton of resources, links to open source hardware tools, anything you can think of, I have on the Open Tools page at elinux.org. And that'll cover links and anything, including these slides, will be up there available to you. So, questions? Yes, Allison. Yes. Absolutely. There are a lot of companies like SparkFun, Adafruit, Seed Studios that specialize in taking a very difficult package such as BGA or QFN and creating a small breakout board to convert it to DIP packages. And most of them are pretty cheap. But really, when you talk about designing your own board, most of the time there's no satisfaction like being able to solder it together yourself in your garage and saying, I built this. And yeah, exactly. Exactly. Um, well, there's one of the popular boards is called Papilio, and it's one of the best design boards out there for FPGA development. And there's some online tools and things, but they're all closed source. There are versions that run under Linux, but it's all as free in beer, not as free in speech type items. And that's one of the reasons I put that up there as roadblocks, is because the tools that are necessary to work with FPGA for open source hardware development and open source development in general are just not there yet. And as a community, we have got to recognize that and start moving in that direction so that we can solve that issue. As far as yeah, I've not actually. The question is, what's it like working with SparkFun and Adafruit and Seed Studios as far as having them build the platform or the device for you? They have most of them have a developer program where you basically upload the files to them, and someone that might want to order one can go to their website and click buy, and when they click buy and they get enough people, like 10 people that have ordered it, they'll go and build it and then ship it out. So there are programs where you can upload your design file, whatever it is that you've created, and people can buy them and purchase them in that way. But in general, what most people do for these types of tools, they'll find a contract manufacturer to build 10 prototypes and things like that. It can get expensive, but if you've got a good soldering station at home, a lot of times if you do it right and use the right devices, you can do it yourself without too much of a problem. Yes, sir. If you have hardware design skills, how can you help with the hardware, open source hardware community? First of all, it's very good to sign up with a lot of the mailing lists, like for instance on SIGROC or OpenOCD or FlashROM. A lot of times people will post their particular hardware design for review, and if you have good, you're electrical engineer and you need to do it would be beneficial for you to review their design and give them feedback. Oh yeah, this is good, but your ground plane is not necessarily as big as it should be, or you've got this labeled incorrectly. Just simply providing feedback, just like somebody would submit a patch to a mailing list. If you're on the mailing list and you can give them some advice to make their design a little bit better, that's very important. Actually, for the hardware review, it's extremely important because mistakes are extremely expensive. Yep, exactly. Yes, sir. That's the question is, are there similar communities for sharing hardware design files? No, not really. A lot of people do use GitHub to share their schematics and design files. Review again. Companies like Adafruit and SparkFun have forums that you can post. There are a lot of people there that are very active and review. Groups that generally design software like FlashROM or SIGROC, they have very strong mailing lists where they will review stuff. But GitHub tends to be where a lot of people post their stuff and just treat it just like a software. Absolutely. And just a show of hands, how many people here are software only developers? So about 40%. How many of you are okay doing your own soldering for through-hole, resistors and through-hole components? So that's nice. So we've got a pretty good mix of hardware folks in here. Um, so if for the software folks, it may seem a little daunting on there to get started, but it's really important. Just like you broke into software development, sometimes you've got to buy a small kit and let the magic smoke out a couple of times, and once you've done that, you learn and move on. So the whole point of this presentation really is so, it has become apparent that the open source community has done fantastic with Linux and other open source projects, and what we want to do is see that transition into open source hardware. Sure. Absolutely. There's several companies that actually sell hot plate and toaster oven modifications so that you can do those yourself. They have a thermal control and everything. Yes, sir. Oh, I'm sorry. Let me get this young lady up front. She's been waiting for a question. There are, that's one of the interesting. The question is, can KiCad use Eagle libraries? That's one of the great things about open source. If if it's open source, most people will end up creating some sort of tools, and there are actually tools that will convert Eagle libraries into usable format for KiCad. No, I've had very little luck on doing that. Yeah, unless you. Yeah. The advantage to using Eagle with SparkFun libraries is you can go to SparkFun and say, I want this LED. I'm going to order 10 of them, and at the bottom of the page is the library for that part. And that is a big advantage, especially for somebody that's new to doing hardware development, may not necessarily know how to create their own footprint and symbol. So if you go to SparkFun and you want to, create a small board for your first time, you have the libraries to get started and get your feet wet. But I agree, there are tons of libraries. It just tends to not be connected. Say, here's the library part, and here's where you order this part, and get it together at one time. Yeah, absolutely. Yes, sir. Yeah, it's the same. It's the same ballpark as software in the aspect, but if you license it under Creative Commons, You have the same legal resources for a software package that you've released under Creative Commons. The other things that you can do, if you give the board a specific name, let's say Dave's widget library device, and I put it on the board. If I'm using that specific name, it becomes a trademark item, and you have to enforce it. But you can prevent other people from using that. But yeah, I mean, we actually see that happening with the SIGROC stuff. About 5 years ago, there was one logic analyzer that had actually an 8051 a microcontroller in it, and one person did that as an open source design, and now that particular design is everywhere in Asia, and it sells for like $7, whereas originally it was selling for 25 or 30. So you have to be very careful to make sure that doing it as an open hardware design, it meets with your goal. I mean, if you're really serious about making money for it, then doing it as an open hardware design may not necessarily meet what you want. It's a trade-off. You just like doing an open source software package. If you put it out there, there's a good probability somebody's going to use it and not give you credit, and you'll have to go through the legal system to make them comply with the license. Yes, sir. Yep. Right. Yeah. It, 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 yeah, it's the exact same process. First, you know, uh, if you're doing like, for instance, a GPL violation, which I've done about a dozen or so, and first you have to show that the device, you purchase the device so that you have a right to ask for the software. Make sure that it doesn't contain the material. The text and per the GPL, and then you have to document the fact that it actually does contain the GPL code that you're going to force them to share or whatever. In this aspect, it's no different from the hardware. You have to buy one of those devices in, take it apart, compare the Gerber's design file between the two to make sure that they're exact comparison, and then you have to go through the legal battle just like you would do a GPL license violation. Right. Yep. Absolutely. Exactly. Yes, because the reference design is only a guide. Usually it's done as a block diagram, and it's not a physical implementation. Now, if you copy exactly their reference design and put it directly on there, then that would be incompatible. That's the biggest thing, because you're copying their reference design. If you're just copying a design note and says, be sure and use a 12 picofarad cap on this signal, that's not an issue. Yeah, absolutely. Yeah. It, again, really what I'm saying here is open hardware has the same connotations and issues as open source. If you go through and pick up source code from a vendor and said, here's my source code and I've got all these license restrictions, you have to be just as careful as if you're using a reference design from somebody and they have the same types of restrictions. Tom? Absolutely. There are. The Open Source Hardware Association has a list of different ones that they recommend and can use. I personally haven't found anything that meets my satisfaction other than Creative Commons right now. I wish there was something better, but until we get some unique personalities that, like for instance, we're involved with GPL licensing text, until we get certain personalities involved in open source hardware text and licensing, we probably won't see something that's as stringent and varying as what we have with GPL. Any other questions? To be honest, I haven't really delved a lot into the 3D stuff or 3D printing stuff. So, you know, what I've read a little bit of things like, for instance, if you take a teacup and you scan it and then you start printing 3D models of it, have you violated their copyright by doing that? In this aspect, we're trying to create something from scratch or based on a reference. You know, someone showing you what a cup looks like versus duplicating that exact same cup is pretty big difference. So I think there is a little bit difference between the two. Yes, you can. They're out of stock at the moment, but you can email them directly. I think they're planning to do a build of them. It basically, although it is primarily geared towards DVI, it works with HDMI as well. It does not support the audio support from HDMI, but you can go through and look at it and debug HDMI DVI. And it's got the EEPROM on there, so you can program your own EDID and pretend to be whatever you need to do. I like Fritzing really for educational stuff, but from my personal preference, I find it not very useful in actually creating your own tools and things. It tends to be more of an educational tool in my mind. My son and my daughter use Fritzing for things and connecting up, but I just don't find it a very useful tool for creating your own stuff at the PCB level. All right, thanks everyone for attending. Appreciate it.